Now, we concluded the last video by observing that the log of the odds of the probability of a team winning a game was roughly linear. Now, because we only have two classes, winning a game or losing a game, we're calling win 1 and lose 0. So the log of the odds of the probability of belonging to class 1 was linear, and I said that this is the assumption that the logistic regression model is based on. So what we're now going to do is reverse engineer this statement and show where that magical sigma function came from that matched our data so well. So the odds of a event that occurs with probability p is p divided by 1 minus p. The log of the odds of this event then is just the log of p over 1 minus p. What I'm now going to do is work through a series of algebraic steps to solve for p here. What I'm going to do is replace the left-hand side of this equation with t. Now I know we're assuming that the log odds of the probability is linear, so t eventually we will replace with some linear function, but for now that's not really the focus. What we're trying to do is isolate for p here. So I'm going to say the left-hand side is t, the right-hand side is the log of the odds of this event. What I can then do is raise both sides to the exponent with base e. So e to the exponent t is equal to e to the log of p over 1 minus p. Now we know that e to the log of something is just that something, assuming that we are working with log base e, which is what we do when we are dealing with logistic regression. What I can then do is take this equation and multiply both sides by 1 minus p. So the right-hand side becomes just p. The left-hand side becomes e to the t times 1 minus p, which becomes e to the t minus p times e to the t. What I can then do is add this term to both sides. So then on the right-hand side, I have p plus p times e to the t, and then divide both sides by 1 plus e to the t. And that result gives me that p is equal to e to the t divided by 1 plus e to the t. To simplify things a little, I can multiply both the numerator and denominator by e to the negative t. And on the numerator, that will give me a 1. And on the denominator, this second term will become 1, and this first term will become e to the minus t. So swapping the order of those, I get 1 over 1 plus e to the minus t. So if we start off with the assumption that the log odds of my probability is linear, then my probability is 1 over 1 plus e to the minus whatever it is I am using to represent my linear function. This function here, 1 over 1 plus e to the minus t, is called the logistic function sigma of t. And so the sigma function that we looked at in our notebook is this precisely, 1 over 1 plus e to the minus t. Since we are using t as our placeholder for a linear function, and we know that we can represent linear functions by x transpose theta, where x is a vector of features and theta is a vector of parameters, I can substitute x transpose theta into this equation for t. I can also replace p with the probability that y is equal to 1 given x, which is what we were modeling this entire time. We are trying to model the probability of winning given your field goal percentage difference. And winning here is just y is equal to 1. And your field goal percentage difference is our feature, x. So going from this equation that we had on the last slide, I can substitute in x transpose theta for t, substitute in the probability that y is 1 given x for p, and there lies our logistic regression model. So the logistic regression model formally models the probability of an observation belonging to class 1 given x, which is some vector of features, as being a linear combination of those features, x transpose theta, passed through the logistic function sigma. Now, this looks almost exactly like our linear regression model, and that's because it is very similar, right? The only difference is that instead of just having x transpose theta, we have the sigma, or logistic function, of x transpose theta. That's why logistic regression is sometimes called a generalized linear model, because it's a nonlinear transformation of a linear model. But that's not really a term that we are going to worry about in this class. And so that explains why that black curve that I plotted with the equation y is equal to sigma of 30 times x matched our values so well. It's because if we work from the assumption that the log odds of our probabilities are roughly linear, working backwards, we get that our probabilities can be modeled using this logistic function, which is precisely what we've done here. And so that's where the logistic regression model comes from.